there, I want to go over some of the more common applications of exponential growth or exponential decay. We have a couple different formulas. They're very similar though, that for what's called simple growth, where things are just changing once per time period. These are some slightly different letters than I used in class. What I'm writing here though is like when I say A of t, what I'm talking about is like an amount of something, depending on how much time has passed. So I'm just using the amount depend on the time, or amount as a function of time here. In class, I had used like the letter B for like the balance, or even like the letter P for population. So it really kind of depends on like what we're talking about here. If it's money or animals or something like that, this can be flexible. Same thing here, like this initial amount can be an initial like principal, like for an investment. Could be an initial number of animals or something like that. So again, the letter here really doesn't matter, just that it stands for the initial whatever. And then 1, so looking at changes from a certain value, so adding a certain percent to it, or even subtracting a certain percent from it. So we're looking at percent growth or percent decay here. We're going to see a lot of talk about that. So the R is the interest rate or the growth rate in this case, or here the R would be the decay rate, the loss rate. But the most important thing about R is that it's going to come to you as a percent, but you need to write it as a decimal, and doing that correctly is one of the more common mistakes that we see with this. And then T is again representing the time. Generally this is in years, but it can change, and we'll see that here in an example. Then we have something that's called compound growth, and this is generally used for like bank accounts where you're earning the interest more than once a year, or things are growing more than once a year. And so we see here that we have this new variable here, n, which stands for the number of compound periods per year. So again, I gave you guys some values and some words in class that you need to know, what number is reflected by that word, because this P will come to you as a number in the problem, the R will come to you as a number of the problem, T will come to you as a number of the problem. So those should be pretty obvious, but then N is going to come to you as a word, and you need to translate that into a number. So let's look at this first problem here. So $10,000 is placed in an account earning annual interest at a rate of 2.3%. To the nearest cent, find the value of the account after 5 years if interest is compounded. So right here, keying in on that word, that we're going to be using this formula, not the other one. So I need to know what the initial investment is, what the interest rate is, and what the time is, and then also what the end value is. There's 4 things I need to know, and the rest will just go in the calculator. And so it's usually pretty easy. The initial investment is what we're putting in, so that's the $10,000. The interest rate is is going to come to you as a percent, and then time, of course, is one thing at the time. So, and then what they're doing here on this problem is they're giving us 2 different end values. So we're basically going to work it out twice and see just what the difference is. The more often you compound it, the more money you should have, but it shouldn't be way more. So go ahead and plug in the things I know. So B equals, so my initial investment's the 10,000 times 1, which again represents the 100% that we started with, plus, so 2.3% is 0.023, and not 0.23. That'd be bad. That's 23%. So watching that percentage, making sure you're doing that correctly. And then we're dividing by something, and then we're going to take that something times our t, which is 5. And so in this case, the something here is this annually. And so if something happens annually, that happens once a year. So our end value is just 1. So essentially it's not going to do anything. But I just need to type that in my calculator. Again, a common error, or I guess kind of the way you think about typing that. And hopefully, again, you're using a good calculator, not the one that came with your phone. So 10,000 parenthesis 1 plus, and then 0.023 divided by 1. And then your caret. And then what you really need to do is hit parenthesis 1 times 5. That's the correct way to type it in. So again, kind of more common mistakes, just it's like the writing of the problem, not writing the decimal correctly. So watching that. And then here, especially if this wasn't a 1, but that we need to force our calculator to do this math before it raises it to a power. So putting that parentheses is really important. So let's see what I get. Oops, I got a way too big. I got $28,000. That's way too big. So I talked to you guys about in class, like kind of judging your answers and saying, saying, oh, 28,000, that's a lot of money compared to the 10,000. I realized I put 0.23 in when I typed in my calculator. And the second time I got 11,204.13076. That's my calculator says. But money has, a certain decimal that we should always use, which is the second place. And then I am rounding this. So about, and then I use the dollar sign, $11,204. And then we always round to the second decimal place with money, so 13 cents. Correct way to write that. Everything's going to be pretty much the same for the next one. It's just going to change the end value, because now we're looking at weekly instead of yearly. So weekly, if something happens weekly, that means it happens 52 times a year. Yes, you do need to know how many weeks are in a year. So again, as I type that, basically all I'm going to do is just replace this 1 here with 52s as I go to type that in my calculator. And that time I got 11,218.44914. So I'm going to say about dollar sign 11,218. Since the 4 has a 9 after, it's going to get rounded up. So 45. So again, the more often you compound, the more money you should end up with, but it should not be a lot more. So notice we only end up with $14 more about. So just kind of judging those against each other. If one of them is way more than the other, it's a good clue that you typed something wrong, or you wrote it wrong. So something to think about. Let's look at the next one. Brand new car is worth $22,000, depreciates 9.5% every year. Benjamin used the equation V, so value as a function of time, 22,000 negative 0.095 to the t power to represent the value of the car for t years. Why is this equation incorrect? Fix this mistake. So what we want to think about is, this will be a simple problem because there's no mention of compounding anywhere. And so I'm looking at one of these. This is talking about depreciation, so this should be a decay problem, so I should be expecting a minus. So I want the initial value, 22,000, so that's there. Then I want 1 minus r, and so seeing that, here's our r, and you put minus, but it doesn't have the 1. And so this is just would decrease over and over again. Actually, this would actually not do that, because this negative sign in here would actually mess this function up completely. It would bounce up and down rather than being a nice smooth curve if we tried to graph that. But yeah, what it is he's missing is that 1. So v of t equals 22,000 1 minus 0.095 to the t power. So the kind of explanation there is that he didn't take it from 100%. So losing 9.5% every year doesn't mean you only have 9.5% left. You have 90.5 left, because 100 minus 9.5 is 90.5. So this is where that gets taken care of. So careful about that. Last one here. The amount of caffeine in a person's body decreases about 15% every hour. Sarah drinks a cup of coffee with 95 milligrams of caffeine in it. I'm actually going to do part C first here. I like to write my equations before I do this. I think it's kind of more typical of what we ask you guys to do, is to go ahead and write the equation first. So I want to think about my starting amount, and this is going to be simple. Again, they don't mention anything about compounding, so I'm looking for simple growth or simple decay. I did say decreasing, so you're looking more at a simple decay type problem. So I need my starting value, which they gave us, is the 95 milligrams. And I need a decay rate, which is here. So I want us to say C of t, so the amount of caffeine as a function of time. So our starting amount is 95 milligrams times 1 minus, since it's decay, then 15.3% is 0.153 to the t power. So again, taking that from the 100% minus 15%. So then I'm going to go up and do C of 1, like A asked me to do C of 1. So as I type in my calculator, I'm going to type 95, parenthesis, 1 minus 0.153, caret 1. Now I don't need parentheses here because there's just a 1. It's not 1 times something, 1 minus something, it's just 1. And so my calculator's not going to be confused by that. It's when there's like complex things, like complex, like something like subtracting, can be enough of complexity to mess things up. So. It says rounded, so that gave me 80.465. Round to the nearest hundredth, it says hundredth is the second place. So that 6 is going to get rounded up. So 80.47, what are we talking about? 80.47 what? Must be milligrams. And if you want to go to close to milligrams of caffeine, might be better. 3 hours later, what are we looking at? So C of 3. So 95, 1 minus 0.153, caret 3. Oops. And that gave me 57.7263, a bunch of other stuff after that. Rounding the nearest hundredth. So 57.73, that 6 is going to kick that 3 up, milligrams. There you go. All right. Hopefully that helped a little bit. See you guys.